Hello, my name is Agustín and I am going to present my project of the subject Deep Learning for Acoustic Signal Processing, in which I have developed a classifier for noise events in meeting rooms. The main objective of the project is to develop a system to identify which noise events are occurring during a meeting at each instant of time. In production, this system will record live audio from the meeting and automatically classify every 2 seconds. There are 3 categories or types of events that we want to classify. First, the typing of a computer keyboard. Second, a conversation or the noise, a conversation of 2 or more people. And the noise of an air conditioning. To implement the classifier, we will need some data. In total, we have extracted 6,000 audio files from different sources and datasets. Before the development of the project, we have analyzed the audio files we have extracted. To do this, we have represented each category of noise by its spectrogram in order to make a comparison between the features of each class. Finally, we have performed 2 experiments. In the first one, we have used a multi-layer perceptron as classifier, while in the second one, we have used a convolutional recurrent network. Before getting into the subject, I want to introduce the state-of-the-art of deep learning in the field of acoustics. In acoustics, there are many areas in which many projects or works based on deep learning have been carried out. To give one example, in the area of speech communication, systems based on clustering and audio embeddings have been proposed to automatically separate voices from speakers belonging to the same genre, for example, 2 males or 2 females. This is only one application of many that exists in all the areas that we observe here. At the bottom of the slide, we see 2 main and recent advances in deep learning, which are the location of sound sources by estimating the direction of arrival, and the detection of sound events. Although there is polyphonic detection, that is, detection of more than one sound event happening at one time, to simplify, we have focused only in this work on monophonic detection. The motivation for this project arises from the need to measure the productivity of team meetings in companies that follow agile methodologies such as Scrum and Kanban. By detecting the noise in the room live, it will be possible to generate metrics reports later on about what has happened during the meeting, apart from measuring other parameters such as the level of attendance, duration, noise level of the meeting, etc. As mentioned above, in the first slide, we have 3 noise categories with different frequency representations. This spectrum in particular is that of the air conditioner. It can be differentiated from the rest because it has characteristics similar to those of white noise. This is the spectrum of the keyboard typing sound. We can observe how the moment a person types the whole range of frequencies, it increases in intensity, generating in this way vertical colored lines in the spectrogram. Finally, we have a spectrogram of a conversation extract. We can notice that the fundamental frequency of the voice goes up and down between 0 and 2000 Hz, depending on the pitch of the speaker. In a first instance, we have chosen a multi-layer perceptron as the architecture of our noise classifier with a series of fully connected layers. We have applied regularization techniques between linear layers as well as a softmax layer at the output for probability computations. On the bottom left side of the slide, we have the training optimization curve of the model. We can see that the model needs very few times to reach the optimal level of performance. In second place, we try with a CRNN with a COMNet of 74 filters and a bygroup of 128 units. In this network, we also applied dropout and softmax in the output layer. as we can see, as the model did not improve from the 25 epoch onwards, training was stopped so that time at that time, as can be seen in the graph. The table on this slide shows the results of the evaluation of both models. We can see that both have very even results and almost impossible to improve. Thanks to the resolution of the project, we have learned to process signals and obtain features. We have also learned how to develop the state-of-the-art audio detection systems. This is all. Please, if you have any questions about the project, you can reach me either by mail or phone. Thank you very much for your attention.